for joining us for the webinar today entitled Smoke Suppression in Phenolic Urethane Bonded Sand Systems Through the Use of Engineered Sand Additives. Our presenter today is Dr. Paula Vivas. She's the R&D manager for coatings, sand additives, auxiliaries, and feeding systems. She's been with ASK Chemicals for 7 years now. I am going to be moderating the webinar. My name is Stacy Clifford, and I am the Technical Product Manager for Coatings, Sand Additives, and Auxiliaries for ASK Chemicals. I've been with ASK going on 25 years. And now I will hand it over to Paula.
Hello all, and good morning to some of you, maybe good afternoon for some other ones. And thank you, Stacy, for such a nice introduction. So today we're going to start with the outline of the talk. I divided this talk in 5 sessions. First, we'll do an introduction about the mold and core making technology and overall the casting process. After that, I'll discuss the motivation, why we did this project, and then followed by how we did the characterization of the sand additive, the experimental approach, and some data that I will be sharing with you. We will also review as a sand additive effects of this sand additive could have in the phenolic urethane core properties, and we'll finish with the summary. So let's start talking about mold and core making. So we all know that in order to have good quality castings, we need to make good molds and cores. It's very critical. For that reason, we had to find ways to create these molds and cores that can serve that purpose. And for that, well, most foundries use silica sand as a media. We're not going to go in all the possibilities that could be, but let's say we want to bind these sand grains together. So we had different ways to do it, and then going to go over this summary here. So the main categories that I will say that are out there and the mechanisms to bind sand together are the green sand and the chemical bonded sand. We had other systems like loose foam and unbonded loose sand, but the most common are chemical bonded and green sand. Now inside the chemical bonded sand technology, we have another subcategory, which is the organic binder systems and the inorganic. Now, for the purpose of this talk, we're going to mainly focus on the organic binders. And the organic binders also have different subfamilies, as I'm showing here. Now, what you can see is that most of them actually are differentiated by the way you cure your resin system, right? So, but for the purpose of today, we are going to focus on the phenolic urethane Novec technology. And in general, phenolic urethane binder systems are excellent choice for foundry and mold core making, as you're probably familiar with them. I'm going to mention some of the advantage of the phenolic urethane. We have the high productivity you can accomplish. We can use them on low levels, so the resin can be used in low level addition, and at the same time, you can accomplish very high tensile strength. They're also very good for making complex geometries. So when we had those complex shapes that need to be designed, this binder system serves this purpose really well. Also for surface finish of the mold, I think they're wonderful for that kind of property. And we also have, we can achieve high tolerance using these binder systems. Now, when we take those molds and core make with phenolic urethane now to the casting process, right? When we're ready to pour the molten metal. Well, the phenolic urethane will be exposed to very high temperatures due to contact with the molten metal. And when they are exposed to very high temperatures, they undergo thermal decomposition, so they get pyrolyzed, and that as a result of that, there's a undesired smoke and emissions. There's been a lot of work, especially for ASK had done on the formulations of PEP SET systems, which is kind of how we refer as phenolic urethane Novec system, our PEP SET systems, on improving this situation with the smoke and emissions. I mean, reformulating has been a big thing, and I think we had gotten some significant progress in some of our binder systems to eliminate some of the smoke and undesired emissions. But still, we have some more work to do, and we keep improving. We want to go toward cleaner technologies every day. That's kind of ASK mission. And for that, that will take us to the motivation of this talk today. The idea is to use an engineered sand additive. So sand additives are used in most foundries for controlling casting defects. So this time, the idea is to have this sand additive serving a dual purpose. So in addition to the high quality casting and eliminating casting defects, we will be able to reduce the smoke. And for the rest of the talk, you probably hear me saying the word DISA. This means dual engineers and additive. I will refer to this proprietary blend of SK that we'll discuss here as a maybe BLMSK later on. So that's just the way we refer sometimes internally and sometimes in the lab. This engineer blend has now been is patent pending. So let's walk through for the rest of the talk on how we develop this sand additive. So first we had to do some bench work. So in our R&D, we just developed a small course, and it's a simple concept. We just like making a mold or a core in an actual foundry. We take the silica sand, we mix it with the sand additive. I always actually suggest this to people. So you had to be sure the sand additive is completely mixed with the silica sand before you add your phenolic urethane binder system. The phenolic urethane Novec binder system has three parts. There is a phenolic resin, then the polyisocyanate, and then we have the amine catalyst. In this case, it's a liquid amine catalyst, which will be used to control the speed of the reaction. The result of that is a urethane bond. That's when you cross-link the polymer. So you form a very nice mold core. Just to show below some examples of the small specimens we use in the lab, so people are familiar with the dog bones. We can make dog bones at different conditions. Always, of course, we use a control specimen, which is the one with no additive, and then we can change the level of the additive to 2, 4, 6%. And later on, I will show why we use certain particular range for this sand additive. So here's the first example, the first observation working with this engineer blend. So if we want to look at how much smoke we are producing, the first experiment you will do in the lab will be to pyrolyze the cores. So we use a muffled furnace. We place the cores around 700, 750 Celsius for about a minute. Then you take that core and you can place it in a ceramic bench in a platform. And as you can see on these two photos, this is actually photos from a video that we made. In the left side, you see the no additive. We try to help the eye by putting a black background and a ruler. And you can see that the no additive shows significant amount of smoke. And on the right side, we have our dual engineer sand additive at 4%. And it's not completely 100% smoke suppression, but definitely is a significant amount of suppression of the smoke in the presence of this sand additive. Now, of course, we needed to do something a little more fancy that just looking at the black background and a ruler. So we wanted to quantify the smoke. And the way we do it, so we use the same approach. We take the pyrolyzed cores, but now we transfer them to a chamber. So I show here in the middle of the pictures, you can see the actual experimental setup. This experimental setup is a vertical stab. Uh, you have a light source and a photodetector facing each other. And when the smoke, due to the core present, start traveling upwards, you will see that the incident light will be scattered by the particles and anything that will be blocking, uh, the incident light. For that reason, then you will have, like a physics concept, you will have scatter light, and which is what will indicate the amount of smoke present in the in the experiment. So when you're going to record this, you will measure the intensity of the scatter light as a function of time. So that means this blue curve here, just a cartoon to understand the data. The blue curve means you have a core specimen that had higher smoke, and then the orange curve means less smoke. That's the kind of data that we'll generate from these experiments. So let's look at some real data. So we analyze 4 samples. So we measure 4 samples here. I actually showing the picture of each of the pyrolyzed dog bone specimen at different conditions. We have a control sample, which is the no additive. We always have that there for comparison. We have 2 levels for the dual engineer SAN additive, BLMSK, 2% and 4%. And we also add a commercial SAN additive just to have another comparison point. So as you can see clearly here, as I explained earlier, so if you have a plot of intensity as a function of time, if you take the area under the curve of this, that will be your total smoke. So if you see here, the green and red curve definitely shows some reduction. So if we want to quantify this a little bit easier, you can sum these individual points and get the area under the core, the total amount, and divide by the intensity as a function of time, sum when in the presence of no additives. When you do the normalization, so you can see at 0%, you had 100% total smoke. As you increase the amount of SAN additive, you will see then there is a decrease on that total smoke. So to determine the smoke suppression, you will do 100% minus this number. That will give you your smoke suppression. Now we were very excited here. I mean, this is exactly what we wanted to accomplish. We wanted to have an additive that was going to help to control some of these smoke and emissions. And this bench work was for us very excited. So we wanted to do the real thing, right? So far I show you that we've done everything with little core specimens, pyrolyzed them, and look at the smoke. So at the SK in our R&D team, we have the advantage that we had a pilot foundry lab. So we had a 300-pound induction furnace where we can pour steel and iron, aluminum. So we decided to make some bigger cores on step cones and then pour some steel and look at what we were going to find for the smoke reduction. So you can see there step cones made, the darker ones are made with the additive. The light color is the one with no additive. And we place them inside graphite molds. The idea with the graphite mold is that we only see the contribution coming from the core in case we want to determine the smoke and emissions. So we want everything from the core, not the mold. At the moment we were going to make these videos for recording this event, we removed those pudding caps. They get removed immediately since they're made also of PEP sets. So we removed them. Let me show you now a video that we make. And by the way, these cores were made just to make Clear here, they were made with round silica sand, 1.2% PEP SET magna, 1215, 2215, and a ratio of 60-40 part 1 to part 2. And the catalyst was 4%, 3401. Let's see if I can play this video. I think, see if this works. So you can see here, I'm not playing the whole video because they're very long, because we're trying to set this up. On the left side, you see the no additive. And on the right side, you see the BLMSK engineers and additive. So I can play it again. So if we went too fast, you can see on the left side, there's a significant amount of smoke when you don't have the additive. And once you place the additive, make the additive in the core, you definitely suppress significantly the amount of smoke. So let's go back to the presentation. Right. All right. Okay, so what you can see, and you just saw in the video, is that clearly there's no question with the additive. We can definitely suppress that quite a bit of smoke there. It took about 8 minutes when we analyzed each of these videos. It took about 8 minutes for the core with no additive to stop smoking, and it took about 3 to 4 minutes for the core actually to stop smoking when in the presence of the additive. So that already give you an idea that what we saw in the lab was pretty in good correlation with what we see actually in the foundry. Now, so far, we had seen the smoke suppression. It works very nicely. Now, the next question that comes to mind is, what are we suppressing? Are we suppressing any of these undesired emissions that we know are there during the casting process, like volatiles or any pollutants? Well, we needed to look at that. So for that, we went back to the lab, took again some of the cores. We make this time, I think, 6 samples, 6 core specimen at different conditions. Some with different sand additives, but all of them were made with the same amount of sand additive, 3%, I believe, in this case. The core conditions were also the same as I have been showing so far during this presentation, 1.2% PEP SET magna, 60-40, 4% catalyst. And this work actually was in collaboration with our colleagues from SK Germany. They do have a custom built mini hook stack set up. And this experimental setup is very interesting. And instead of what I showed earlier for the smoke, they actually collect the byproduct from the pyrolysis and they transfer it to collection glass tubes. And they take these byproducts and they analyze it in a chromatography instrument. So that really helps to determine what kind of species are living on the smoke. On the plot on the right are the results from the experiment. We have that if you look at the y-axis, which is the species found in milligram per kilogram core weight, you can see that the no additive had the higher emissions. Benzene, toluene, xylene are the BTX, and the naphthalene is what people call polyaromatic hydrocarbons, I believe. That's the naphthalene. And there's a lot of studies already done by different people that show these are the highest species. They are kind of concerning for health issues. They are present on the casting process. So we are excited to show that in the same fashion as the smoke suppression, we are able to reduce some of these emissions with the engineered blend BLMSK. Again, here is ASK additive that we had, the Beno Ultra 350. We currently is a additive we use for steel applications. It's commercial. We had 2 more commercial additives here and a typical black iron oxide, just to illustrate where we are with respect to typical additives. So at this point, we had shown we can suppress the smoke, we can suppress and reduce some of the these undesired BTX and naphthalene type of uh, emissions. So we have to answer a different question now. We are developing a SAN additive, and when you're working in developing a SAN additive, especially for us in ASK, we look in details a lot of aspects of this, because when you put a powder that is finer than sand, you need to be careful not interfering with properties like tensile strength, the reaction of the speed of the reaction, and the most important thing also, it needs to serve the purpose of eliminating veining and metal penetration, and in some instances it should help with the surface finish. So independent of the smoke and emissions, it needs these additives that we develop needed to uh, help with this, and kind of so we needed to validate this. So let's look at each of them. So the tensile strength, and this is well known that for most sand additives, because they are finer powders, and they also, the nature of these powders are, they had high surface area, they're fine, is known that they could have a reduction in tensile strength. And so that's why when you develop a sand additive, you had to do quite a bit of homework on trying to adjust the distribution so it's less detrimental to the tensile strength. So let me show you here two different time points for tensile strength. We pick 1 hour and 24 hours. Of course, we can monitor other time points, but just to illustrate here, you can see no additive, and this is sort of course made with, again, 1.2% magna, 60/40. We have 0% no additive and 3% for the rest of the samples with sun additive. And you can see that we're not surprised about this. There is a reduction on tensile strength from the use of the sun additive at 3%. But the way we recover our tensile strength is by adjusting the catalyst to a different catalyst with maybe higher active ingredients. So that we have now 3501 here, and then we already kind of back into where we want to be. Remember, the error, these tensile experiments are probably 20%. So we were very pleased to be able to recover the tensile strength of the core without had to increase the binder level. And what I want saying this, because if you think about it, if we had to increase the binder, we will had to have kind of more like a chicken egg situation, where more binder, then more smoke, and then more additive, and then reduction of the tensile strength. So we don't want to fall in that cycle. So the idea is that we can recover the tensile strength by just adjusting the catalyst or the type of catalyst. And we also found some catalysts that didn't work very well. So uh, if we do this in some customer or facility, we will have to work closely to determine the most ideal conditions for catalyst and binder to get the best of we can obtain. Now let's look at the speed of the reaction. So in a PEP SET system or phenylyurethane novate, these are two aspects that I think are very important. So when you mix your sand with your binder, you're gonna have you're gonna have certain time where you can mix, you can work with the aggregate, but it's gonna start curing, it's gonna start hardening. So we have 2 points in time, which is what people define as the work time, and that will be the amount of time available to work with the sand aggregate before start hardening. So you don't want to get there. You want to try to work before that time and make hand run your sand or whatever you're doing. And then after that, once you pass that time, now you had to watch for the strip time, which is the time where you had achieved certain strength so that you can safely remove your core or mold from the pattern safely. So on the right side, again, that's the same condition as I show for tensile strength. For no additive, we're around 6 minutes. So when we put the additive, and this is what we expected, we were going to slow down the work time. But again, we just adjusted the catalyst to make this work again back. And actually, it was interesting because we didn't change the percentage of the catalyst, and we were able to actually speed up a little bit the work time. So that means we could probably use 2% of this catalyst and get back to where the no additive conditions are. Again, there's some catalysts that we found not very helpful in this case, like the 330 didn't really help here. And the same applies for the strip time, they're kind of correlated. So if you could adjust the work time with a different catalyst, make it work, it's going to work for your strip time. So what's the next feature that the sanity needs to have to be a good sanity, right? Well, the anti-binding functionality needs to be there. So for that, we need to go back to the foundry and lab and do some testing. So we took some of our step cones that we make earlier, but this time we placed them in PEP SET molds and just did a normal pour. And the result of these castings now are showing on the right side. We cut the step cone casting in half, so you can see the inside of the step cone. So for the no additive, we had quite a bit of veining. I mean, it's pretty dirty casting. You don't see in this case, for this particular example I'm showing here, you don't see that much metal penetration, but sometimes we get pretty bad penetration. Um, so in this case, I'm mostly seeing veining, but you can eliminate all of that veining by just adding the 3% BLMSK to an engineers and additive. So that's pretty exciting because so far uh, the conditions for a good sand additive are kind of achieved here. So we're able to clean the castings. So in summary, I will say we had successfully developed a dual engineer sand additive that can had and produce high quality castings. It can reduce the smoke. And on the other hand, the other properties of the phenolic urethane Novec mold and core technology can be adjusted to make this whole process work smoothly and without any issues. So far, the tensors can be adjusted, the reaction speed could be adjusted, the elimination of the veining metal penetration and improved surface finish was accomplished. And more exciting, we had the smoke and addition reduction, which will be the new benefit from the use of this sand additive. Of course, I can finish this talk by acknowledging and giving thanks to the people who work with me really hard on making this project uh, to come to a successful end. We have in my R&D team a lot of good scientists, and especially I want to thank Matthew Schaffner. He did lots of smoke testing and tensor strength. He worked really close with me on this. I want to thank Merrick Simon, who is our technical product manager for Metallurgic. He, beginning of SK, really helped me, along with Glenn, for setting up the foundry testing and smoke suppression in the MAL lab, the metal application lab. And also last, Dr. Wolf Wirth for his support on the BTS emission testing in Germany so that we could characterize that part in the project and get some idea what we're measuring in terms of emissions. And with that, I think we can discuss some questions.